Okay, one last video for this week. I want to talk about interference between waves. And this is something that we talked about in the context of waves on strings. But talking about it with sound waves, it's a little bit different. The one thing is that sound waves propagate in 3 dimensions. And so the interference between waves is different because you can have 2 point sources that interact, and it's a different interaction than one-dimensional waves on a string. The other aspect we'll talk about, and I'll do that first here, is the interference between 2 waves with different frequencies. So let's start with that. So I have, this phenomenon is called beats. Okay, so if I have 2 waves with different frequencies, so I'll just write down the displacement function for wave 1, there's some amplitude. I could do sine or cosine. I'll choose sine. Omega 1 t, and we'll say that x is equal to 0, so we'll ignore it. We're just going to sit in one point in space and watch the waves come by. The second wave will have a different frequency. Okay, and if I consider these two waves, so I have one that's got one frequency like this. Okay, so this is wave 1. So wave 2 might have a lower frequency, so it's kind of looking like that. Okay. Now what I see is that the relative phase between the 2 waves. So what I'm going to do is add these 2 together. So these 2 waves are passing by one point. I'm going to add them together, and what I'm going to find is that the result will be a pattern where the amplitude of the 2 waves added together varies in time. Okay. Now maybe I'll start with the mathematics. So if I consider adding these 2 waves together, again, you could do this with complex exponentials. I have to go to the next page here. So if I have sine of some quantity a plus sine of b, and again, you can prove this with complex exponentials, you can show this is the same as 2 sine a plus b over 2 times, sorry, that's a cosine there, cosine of a minus b over 2. And so in our particular case, we're going to have d1 plus d2 is going to be 2 times the amplitude. I'm assuming here they have the same amplitude of sine omega 1 plus omega 2 over 2 times t, multiplied by cosine of omega 1 minus omega 2, if I can squeeze it in here, over 2 times t. I didn't do a good job there. Okay. So let me fix this. Okay, and say times cosine omega 1 minus omega 2 over 2 times t. Okay, so that's the mathematical result of adding these 2 waves together. I'm sitting in one point. I have waves of 2 different frequencies washing over me. So what I can do is now demonstrate this with an applet. So what I have here is a wave of 1 frequency, and I can hear it. Hopefully you can hear that. Okay, there's 1 frequency. Okay, then I can have a second wave with a slightly different frequency, a little bit higher. It's hard to hear the difference actually. But now if I put them together, the result looks like this down here. This is the sum of the 2. And this is what it sounds like. So you get what sounds like a modulated amplitude. And that modulated amplitude comes from this second term. Okay, that's the difference frequency. So you see this, what looks like a low frequency oscillation and then high frequency oscillation embedded. So this low frequency is omega 1 minus omega 2, and in this case that's only 3 hertz. And then on top of that you have this much higher frequency, which is the average frequency, okay, between the 2. And you get this adding together. And so what's happening is, if you go back and look at my picture from the previous page, if I can do that. Yep, there we go. Okay, and I need to move this out of the way. So if I add these two together, the sum is going to vary with time. So at this instant here, they align up pretty well. So you're going to get constructive interference at this point. But over here, you see I get destructive interference as the waves come through. And so this point is going to be the point where I get the near zero amplitude in the wave. And then as the waves move on in time, I go between complete destructive interference to complete constructive interference, and I oscillate back and forth. So I get this beating phenomenon where the two waves beat together. I get basically a modulation of the amplitude of the wave with time as a result. Okay, those who play stringed instruments, you play a guitar, the beat frequency that you hear here can be used to tune guitar strings. So it turns out that neighboring strings on the guitar will have common frequencies when you finger them. And so you can use one string to tune the other ones. And so if you play them together, if the frequencies don't match, if they're slightly different like these two are, what you'll hear is this beating between the two strings. And what you do is you tune your string to get rid of the beat. So if I go to the same frequency, of course, both strings add up to the same sound and I hear no beat. But if I'm slightly detuned, I'll hear this beat. Okay? And I can go the other way and hear the same thing. Okay? And if they're really detuned, like here, I'll hear a very rapid beat, okay, because of that difference frequency. Okay? All right, so that's when you have interference in time. Two slightly different frequencies can create this beat pattern due to interference. Okay, let me talk about interference in space now, and that's something that we talked about for waves on strings. So we have these two waves that add together to form a standing wave, for example. Now the difference in sound waves, so this is interference in space, is that sound waves propagate in 3 dimensions, okay, from a point source. And so if I have 2 point sources that emit waves, here's one, here's another. So we draw it as phase fronts, right? So as these fronts overlap, and remember these fronts you can think of them as sine waves going off. As these, oops, I didn't do a good job there. As these fronts overlap, at different points in this plane, they will meet with different relative phase, okay? And so you can get constructive or destructive interference, and it'll depend on where you sit in space. So if I'm sitting over here, I might hear constructive interference. I sit over here, I might hear destructive interference, depending on the difference in path length. So what matters is if I look at a point in space, the question is, how far away am I in wavelengths, okay? So I basically count up the number of wavelengths. That tells me the relative phase of the two waves as they meet. Okay. Well, let me just state that mathematically. I'll come back to this issue conceptually in class, and I'll say a bit more about it in this video. But now I'm going to consider the case where I have 2 waves, and I'll write the displacement again. Same amplitude, same frequency, same wavelength. Okay. So I have sine of k. Now what I'm going to do is consider this location here, and the point is that the distance, so this is source 1, this is source 2. Let me pick another color to make this easier to see. The distance from point 1 to this location I'll call x1, and the distance from point 2 to this location I'll call x2, and those are different lengths. Okay, and so I'm going to have a different amount of phase change of the wave, different number of wavelengths fit in x1 versus x2. So when the two waves arrive at this location here, they'll have different phase, okay? And that means they'll add together differently depending on the location that I choose. Okay, so d1 at that location will be sine k x1 plus omega t. And I might have an arbitrary phase that I offset the two, but I'll ignore that for now. I'll assume that both waves leave the source at the same phase. Okay, so then I'll have d2 is kx2 plus omega t. Okay, and so if I now add these two together the same way that I did the the beats in time, I just use the same formula. And so what I get is the total displacement due to the wave is twice the amplitude times the sine of the sum. Okay, so I'm going to have k x1 plus x2 over 2. And then I'm going to have minus omega t. And then I'm going to multiply that by cosine of k x1 minus x2 over 2 minus omega t. Okay? And I'm sorry, the omega t's, in this case, the omega t is going to add and stick around. In the second case, oops, I meant to have an eraser here, because the omega t terms are the same in both, when I subtract them, they just cancel out. And so what I get, that's very important, what I get is that this term looks like an oscillating wave, and this term is a stationary pattern in space due to the interference of the waves as they arrive at that location. So it doesn't matter, it doesn't oscillate in time. I get either a constructive or destructive interference. I get a pattern in space due to these two waves coming together. Okay? So this is mathematically what the interference pattern gives me, is this modulation of the amplitude plus or multiplied by the oscillating wave. Now let me show that to you in a video, okay, in an applet. So what I have here are two wave sources, and both are emitting sound waves. Okay, so I separate them here. Each one is emitting circular wave fronts. Unfortunately, it's going to slow down now. Let me go back to where I was before. Okay. If I put them right on top of each other, it'll look like one wave source. Okay, so here's one wave source where I just see circular waves coming out. Now as I start to separate them, what I see is that I get wave pattern. So although it's going slow, the waves are propagating out from each source. But I see these locations in between here where the wave intensity is always gray. And wave intensity being gray in this case means zero intensity. So at these locations here, the waves always add up to destructively interfere with each other. And you get no wave amplitude in those locations. And what matters is the separation between these two points in space, these two source points, as a function of the wavelength. So if I put them so close together, as I did before, that there's no wavelengths between the two, it's difficult to develop this interference pattern that I'm showing you here. Okay. All right. I'll spend more time explaining this in class, but I wanted to just show you this picture. I'll show it again in class, and then write down this equation and talk about it a little bit. But we'll talk more about the concepts in class. So let me stop there.